Great, thank you so much. Hello, and thank you for attending today's guest speaker session. I am honored and privileged to welcome Dr. Seth Darling. Dr. Darling is the director of the Center for Molecular Engineering and a senior scientist in the Chemical Sciences and Engineering Division at Argonne National Laboratory. He also serves as the director of the Advanced Materials for Energy Water Systems Energy Frontier Research Center. He received his PhD in physical chemistry from the University of Chicago. His group's research centers around molecular engineering with a current emphasis on advanced materials for cleaning water, having made previous contributions in fields ranging from self-assembly to advanced lithography to solar energy. He has published over 125 scientific articles, holds a dozen patents, is a co-author of popular books on water and on debunking client skeptic myths, and lectures widely on topics related to energy, water, and climate. Please welcome Dr. Seth Darling as he presents The End of Water as We Know It.
Thanks very much. Hope everybody's doing well. And hopefully you can see my screen. Maybe someone can give me a thumbs up just so I know you can see that. Great, thanks very much. All right. So yeah, today I'm going to be telling you about water, and I'll make sure I stay within the 40 minutes so that there'll be some time for questions at the end. So water. This is a substance that is diverse, it's powerful, and it's essential. You can't have great coffee without great water. You and I are actually mostly water. If you measure it by mass, it's about 60%, but if you count the molecules, it's actually more than 99%. So when we talk about water, we really are talking about you and me and every other living thing. Water controls our weather. It's carved many of the landscapes we see around us, including the Great Lakes that are just a few blocks from where I'm sitting now. More pertinent to today's times, you and I are washing our hands with water. Water has dictated the rise and fall of many of the great civilizations through human history. Just a few examples pictured here at the top. That image is meant to represent ancient Egypt. And you may know in ancient Egypt, there were a series of kingdoms. It wasn't one continuous leadership chain. And each one of those kingdoms rose and fell with plentiful or shortages of water. And in fact, the ancient pharaohs of Egypt retained their power by their knowledge of water and when the Nile would be flooding or not. The image in the center is from the ancient Roman Empire. The Romans were some of the great water engineers of history. The aqueducts, like what you see pictured here, actually brought enough water to the ancient city of Rome that per capita, they actually had a water supply as large as what we have in the modern United States. Really phenomenal given the point in history that was. Another great innovation they had was something called fit for purpose water, meaning they actually had different purity streams of water for different purposes. You don't need super clean water for a fountain in public display, but of course you would want pure water for drinking, and they actually had separate streams for those purposes. We got away from that idea somewhere along the line in history, and just today we're starting to get back to it because it actually was a fantastic concept. And pictured at the bottom there is an image from ancient China, and that is a map of what's called the Grand Canal, which is still the largest canal of its kind in the world. And what it did is it linked the Yellow River system in the north, dry part of China, with the Yangtze River system in the south, uniting ancient China into a militarily defensible state for the first time. Water technology has also been behind many of the revolutions that have changed human civilization through history. One example would be transoceanic sailing, which globalized civilization for the first time. Water wheels were what launched the Industrial Revolution, harnessing the power of flowing water. Watt's steam engine revolutionized transportation and a number of other industries. The sanitary revolution in the 1800s expanded human lifespans longer than any other innovation through human history. Giant dams like Hoover Dam, pictured here, finally gave humankind control over Mother Nature's fickle precipitation patterns and flooding. This not only provided plentiful electricity for initially the United States and then around the world through hydropower, but probably even more importantly, it dramatically expanded our ability to do agricultural production, which is really what launched the United States to be a global superpower in the middle of the previous century. And more recently, back to the oceans again, shipping and intermodal shipping containers revolutionized global commerce. In fact, 90% of global commerce today happens on water. So we use water for a huge number of things, and it's really central to society in so many ways. I normally like to ask an audience this question, but in a Zoom platform, it's a little more difficult, so I'll give you the answer. But I usually ask, what do you think the largest single withdrawal of water in the United States is? And typically an answer might be agriculture, farming, which indeed withdraws a large amount of water, but the answer is actually power plants. This is by far the largest withdrawal of water in this country. It's about half of all the water we withdraw is for the generation of electricity and power plants for cooling, and to a lesser extent for the steam generation to turn the turbines. So we use a huge amount of water to make energy. This is one key connection between water and energy, but the flip side is also true. We actually use a tremendous amount of energy to treat and distribute and use water. This is the single largest consumer of electricity in the United States. So that connection between water and energy is sometimes called the water-energy nexus, and there are many ways in which these two sectors are intertwined. I've only given you a few examples of that, but there are plenty of others. So water is so central to everything about life and society, and yet in some sense, water's invisible. It's actually hidden all around you in the room where you're sitting right now. And let me explain what I mean by that. If you take 683 gallons of water, that will allow you to grow 6 pounds of alfalfa hay. And if you take those 6 pounds of alfalfa hay and you put them into a machine that looks like this, it will give you 1 gallon of milk. So 1 gallon of milk doesn't look so large, but in a sense, it represents nearly 700 gallons of water. And it's not just milk or dairy, it's all food. You take a grape, not a bunch of grapes, one grape represents about 1/3 of a gallon, a single walnut, about 5 gallons, one potato, more than 6, a cup of coffee, and this is not a latte, we're talking just one single serving of black coffee, about 37 gallons of water. If it were a latte, it would be a much larger water footprint because I told you dairy is very water intensive. For example, one serving of Greek yogurt is about 90 gallons of water. And the most water intensive food of all is meat, especially beef. For example, one hamburger is over 600 gallons of water. But it's not just food that represents water. It actually takes water to make anything. All of the raw materials that we use, paper, cotton, plastic, steel, you name it, none of them can be manufactured without water. What that means is that the clothes that you're all wearing, the smartphone in your pocket, the cars driving by on the street outside, all of these things represent huge amounts of water. Now, there, of course, are not literally 40,000 gallons of water in a car. What this is called is virtual water. It took 40,000 gallons of water to make the materials that make up the car and to put them together to make the car. So there's a really important point about water here, which is that you can't actually move large amounts of water over large distances. So, I sit here near the Great Lakes, and we have right in this country lots of places that are extremely water stressed, especially in the American Southwest. We cannot feasibly move a relevant amount of water from the Great Lakes down to, say, Arizona. But we do move goods around the world all the time, whether it's cars or phones or clothes or food. And so what we're doing is we're moving virtual water around the world. And there are countries that are net virtual water exporters and countries that are net virtual water importers. And it lays out somewhat like you might expect based on water supply. So regions that tend to be drier tend to be virtual water importers, largely in the form of food. Just one example of how this plays out, there's a dairy company based in the Middle East called Al-Marai, which is Arabic for the pasture. And the pasture in this case is not in Saudi Arabia, it's in places like Argentina, which, as you can see here, is a net virtual water exporter. What Al-Marai does is it grows hay in Argentina using groundwater. Incidentally, groundwater is a topic we'll get back to shortly. And then it exports that hay back to the Middle East to feed dairy cattle to produce dairy for regional consumption. So that is a large movement of virtual water from South America to the Middle East. And that's just one example. This kind of movement of virtual water happens all over the world on a massive scale. And to the best of my knowledge, there is no international oversight in this process of the movement of virtual water. That's something that's going to have to be revisited going forward as water becomes a bigger and bigger stress. So as you can tell from that map, an interesting question to ask is, where is the water on Earth, since we move virtual water around so much? Well, this is a pie chart showing you, first of all, what is the breakdown of salty water, saline water, versus fresh water. There is a lot of water on Earth, a tremendous amount of water, but almost all of it, 97%, is in the oceans. And that seawater cannot be used directly for almost any of our water needs. You can't drink it, you can't water crops with it, you can't manufacture steel with it, and so on. So only 3% of Earth's water is fresh, but that's actually still a lot of water. However, let me zoom in on that little pie slice that is the 3%. It turns out that most of that is actually frozen in ice caps and glaciers and so on. That's inaccessible water. We can't really use that frozen water. Pretty much all the rest is under the ground in groundwater and aquifers. And we are using that, but in almost every case where we're using groundwater, we're using it unsustainably, meaning we're extracting the water much more rapidly than it is being replenished, which means it's going to run out. And that is true in aquifers all over the world. A good example from this country is the Ogallala Aquifer in the Great Plains states, which is rapidly being depleted and is one of the major sources for irrigation for the food that we eat in this country. Now, on this pie chart, you might not even see it, but there's actually a tiny little sliver of water left. That is all of the fresh surface water on Earth. So that is that tiny a fraction of that little tiny 3% pie slice of all the water on Earth. This is really a phenomenally tiny fraction of the water that is on the planet. Oh my gosh, that is the water that most of us rely upon. So there is a huge supply concern when it comes to water. Turns out that the demand side is also a big challenge. So the world's demand for water is not going down, it's going up. And this is in part because of population growth, but it's actually more so because of development. As each individual starts to use more water, not directly, but in the form of virtual water, because they're consuming electricity and clothing and cars and other things. So as China and India and later Africa, Brazil, these countries develop more and more, the per capita demand for water skyrockets. So by the year 2050, it'll be 50% higher demand than it is today, while at the same time supply is diminishing. And there is no substitute for water. We fight wars over oil, but there are substitutes for oil, no substitute for water. What this means is that water really represents a massive global risk. There's this fascinating report that gets produced every year by a group called the World Economic Forum. You can find these reports for free online. This is the cover from the one from last year. And in every one of these reports, there is a table they produce, which I've shown here, or rather a chart, where they're plotting the risks, where one axis is the likelihood that this thing is going to be a huge disruption for society, and the other axis is how large that disruption might be. So if you're in the upper right part of this plot, those are the biggest risks we face going forward. And there's water crises way up at the top of this chart. This is literally one of the biggest risks we face as a society. And just again, for a relevant context for today, That point right there is the spread of infectious disease like COVID-19. And you can see water crises are evaluated as a significantly higher likelihood and much larger impact. And you've seen the impact that something like COVID-19 has. So, you might think that someone trying to stress the importance of paying attention to water is kind of a tree hugger type person. This is an audience of sustainability folks, so I'm sure you're all on board with this. But it's not just kind of the environmentalists of the world who are sounding the alarm about water. You may remember the movie from a few years ago, The Big Short, which was a great movie. If you haven't seen it, it was about the global financial collapse in the late 2000s, which, as you'll remember, was based on the housing bubble. And in that movie, there's a character, he's played by Christian Bale. This is, of course, based on a true story. Christian Bale's the guy on the left there. And the real person he was portraying is a guy named Michael Burry. And Michael Burry was the guy who saw the problem in the housing market before anybody else. And he invested a tremendous amount of money in the fund that he managed and ended up making billions of dollars for himself and all of his investors. So this is a guy who recognizes huge structural financial problems in the world, typically before other people. Now, at the end of this movie, The Big Short, there's some text that flashes up on the screen. And what it says is that Michael Burry is focusing all of his trading today on one commodity. And given the subject of this talk, it won't be a surprise to you what that is water. Interestingly, what he's actually investing in is virtual water. So he recognizes this is going to be a huge source of strife going forward, and therefore there's a huge financial opportunity. Now, if we're going to mitigate this kind of threat of conflict over water, it's going to require cooperation. And water cooperation goes back a long time. This is not a new concept. We can go all the way back to the early days of human civilization in Mesopotamia, the ancient civilization of Sumer, the Sumerian civilization, which was in the Tigris and Euphrates system. There were these two city-states, Umma and Lagash, that were only 20 miles apart. And they were constantly fighting over water, a stretch of the Guadena River, which is a tributary coming off of the Tigris and Euphrates system. And the ruler of Sumer at the time, Mesalim, came down and kind of put an end to these, the bickering between these two city-states. And he had them build a trench with a levee on either side, which kind of set the border, like you draw a line in your kid's room and you stay on this side and you stay on that side and stop fighting. Turns out that this treaty was not only the first water treaty back in 2550 BC, but it was actually the first recorded treaty of any kind. So treaties start with water. Now, just to kind of drive the point home about conflict though, it's about 100 years later that this all fell apart and Umma and Lagash got into a full-fledged war, which is the world's first water war, where they started diverting water away from their rivals. This was far from the last water war. In fact, there are some low-level conflicts that are going on today, and there will be many more going forward. And this is because, in part, so much of the water source that we have on this planet doesn't pay attention to the political boundaries that we draw between nations or between regions within a nation. It crosses boundaries, these sort of artificial human boundaries. And there are countless examples of surface water, rivers and lakes that cross international boundaries, but also groundwater, those aquifers that we access. There are almost 150 countries that rely on these international basins. Keep in mind, there's fewer than 200 countries in the world, so this is almost every country. What that means is there's going to be a huge amount of conflict going forward based on water. This is a map of river systems around the world that cross international boundaries, and you can see it's pretty much everywhere. Huge numbers of river systems that cross international boundaries, and the same goes for groundwater. This is a map of transboundary aquifers, also all over the earth. So a bigger concern might not be just where is the water, but actually where is the water stress? Because of course, if the water, even if it's transboundary, is plentiful, like the Great Lakes, that's not going to be a huge driver for conflict. But where there's water stress, is where you're going to have a big impetus for conflict between nations. Now, it turns out that water stress is also all over the place. So this is a map color-coded with the darker red being higher water stress regions around the world. And you can see this is not isolated to just a few of the dry regions like you might have expected, say, for example, in the Middle East, but it's actually all over the place on basically every continent. Almost everywhere there are people. And it's getting worse because of climate change and numerous other factors. You've probably seen the stories just a few years ago, Cape Town, South Africa. This is the capital of a major industrialized nation, literally almost ran out of water. They were days away from running out of water before the rains came and saved them at the last minute. Even more recently, Chennai, India, just last year, almost ran out of water. This is going to happen more and more as we go forward. And it's not just water supply, it's also how you go and find your water. So we are accustomed to just turning on a tap to get the water we need in our homes for every day. In many parts of the world, India, large parts of Africa, other places, people have to go and fetch their water from a source, whether it be a well or some other source, which is often quite far from their home, on average more than a mile away. And I don't know if you've ever tried to carry any significant volume of water, but it is very heavy, which limits how much you can carry over such a distance. And the burden, unfortunately, on this carrying water for residential needs is borne almost exclusively by women and girls in these nations, where they literally have to spend hours every day trudging to the water source and bringing back all of the water that is needed in their home for that day. Oftentimes, more than one trip, these girls end up not being able to go to school because of this, and therefore they're at a disadvantage for life relative to their male siblings. And it's not just water supply, it's also the quality of the water. One of the most tragic statistics related to water today is this one. Every 90 seconds, a child somewhere dies because of a water-related disease. These are completely preventable deaths, and it's a true tragedy. So the challenge with water is that usually you're going to have to pick two of these three attributes. Finding water that is safe, cheap, and plentiful is almost impossible. It's very rare to find this around the world. You typically can pick two. So finding safe and cheap water, as I said, is really rare. That's not a plentiful option. We have that here near the Great Lakes, but in many parts of the world, most parts of the world, this is not the case. You can often find cheap and plentiful water, but that water is very low quality, whether it's from the ocean or from some polluted source. And we have plenty of ways to clean up water. You can take filthy water, it can be seawater or polluted water, and make it clean, but that costs money. So safe and plentiful is not going to be cheap. So we've got a real challenge with water, and yet, as I told you, in a sense, water is invisible. And this is not good for us or for water. What happens is, because in a sense it's invisible, we don't think about it so much in our daily lives, we often take water for granted. A few years ago, if you had stayed at a Four Points hotel by Sheraton, the little bottle of water that came in your room had a placard on top of it that said this: "It's water, of course it's free." Now, what they were doing was, sort of poking fun at the hotels that charge you whatever, $5 or $8 for a bottle of water in your room. But what they were really doing was tapping into this sense we have as humans that water is plentiful and it's everywhere. It should be free. Why do we have to pay for this? And that's one of the reasons, I think, why we take water for granted so much. Turns out we're incredibly wasteful with water. We spend a lot of energy and money cleaning up water to make it drinkable, and then we pump it into our water mains. And on average, 1 in every 6 gallons, that is a huge fraction, that we pump into those water mains is just lost to leaks in the system. Those water mains are a disaster. They're old, in some cases a century old. They're deteriorating, and water just leaks out into the ground. If those water mains were up on the surface and we saw these leaks, there would be people screaming for new infrastructure, but because it's hidden, it's kind of an invisible scourge. It's not just water supply that's so poor in places, including right here in the United States, it's also water quality right here in the United States. I'm sure you're all familiar with the disaster that happened in Flint, Michigan just a few years ago with lead in their pipes. This is also a huge challenge in lots of other places, including right here in Chicago, where I'm sitting. But it's not just in a few places that have old lead pipes. It turns out that all over this country, there are challenges with water quality coming out of the tap. About 15% of Americans have tap water with a documented health-related violation. There's a fantastic book by a friend of mine that I recommend. His name is also Seth Siegel, much more popular author than myself. He wrote this most recent book called Troubled Water, What's Wrong with What We Drink. And it's all about exactly this issue about kind of the quality of drinking water, especially in the United States, he's focusing on, and sort of how we got into this mess and what we need to do to get out of it. So I encourage you to check that book out if you're interested. Now, fixing this problem is going to be really expensive. We have underinvested in the water infrastructure in the United States for many years. However, let's put that cost in context. So it's going to cost about $24 billion a year for the next few decades to fix this problem, to fix all those leaks in the water mains and to make sure that we have clean and healthy water coming out of everybody's tap, which is a lot of money. However, we're actually spending over $30 billion a year on bottled water in this country. That is absurd. Bottled water makes no sense for all kinds of reasons, but right here you can see we are already spending the kind of money we need to on water to fix this problem. We're just spending it in the wrong way. So I love this quote. It's an old quote from Ben Franklin in Poor Richard's Almanac when he said, "When the well is dry, we learn the worth of water." We think of water like it should be free, but when it's taken away from us, we realize just how valuable that water is. In fact, there probably is nothing more valuable, and we need to start rethinking that. So I'm a scientist. I would be a failure of mine if I didn't go through a little bit of science about water. So what is water? This is the structure of a water molecule, and I would typically ask an audience, what is the chemical formula for water? And I'm sure you all know the answer, because this is the one chemical that everybody knows the chemical formula of. Water is H2O. So that's 2 hydrogen atoms and 1 oxygen atom. So you all know the chemical formula, but what you may not know is that the molecule looks like this picture here, where the red ball is the oxygen and the 2 white balls are the hydrogen. And you'll notice that the geometry of this thing is such that it's bent. The 2 hydrogen atoms are on the same side of the molecule rather than being in a straight line. That feature of water turns out to be really important because, like every molecule, there are electrons swarming around these atoms, and turns out oxygen likes those electrons more than hydrogen does. And so as they're swirling around, they spend more time near the oxygen than they do near the hydrogen. And you get a feature that's called polarity, where one side of the molecule is slightly more negatively charged because the electrons are negatively charged than the other side. So it's polar, like what's shown here. And that one feature of water, the fact that the water molecule is polar, controls a huge number of really important things about how water works. And honestly, without it, life would not exist anywhere. One example. You and I and all life forms are made up in large part of proteins. Proteins do so many things for life. And proteins are these big, complicated molecules, long chains of amino acids that fold up into extremely complex shapes. And it's the shapes of the proteins that really give them their function, that allows them to do everything they do in our bodies. So how does this molecule know to fold up into this very specific shape to give it that very specific function? It's all because of water. So those amino acid chains have charges on them, positive and negative charges along the chains. And the way that those charges know how to interact with each other is that those proteins are surrounded by a sea of water molecules that are polar, having those positive and negative sides to the molecule, that kind of mitigate all those charges and direct the protein how to fold up. You take away the water, the protein will not be folded up. It will have no function whatsoever. It requires the polarity of water. Without this, again, you wouldn't have life. Water's polarity also leads to this very unusual feature of water, that solid water, ice, is less dense than liquid water. May have to pause for a moment and think that that's very rare for a material, for the solid to be less dense than the liquid. In fact, I only know of maybe five materials in the world where this is true, and all of the other ones are just single elements, things like germanium, some weird stuff on the periodic table. Water is the only molecule I know of that does this. So it's really pretty weird that ice is less dense than water. And yet, if this were not true, again, we probably would not have life on Earth, because what happens in cold climates, in bodies of water, which remember is where life started, when the water starts to freeze in the winter, that ice floats up to the surface because it's less dense, like pictured here in Lake Michigan in the winter, and that forms a protective insulating barrier at the surface, which prevents the entire lake from freezing when temperatures are so cold, and thereby life can continue to exist in that liquid water through the winter months. Water were not polar, this would not happen. We probably would not have life for that reason also. Water's polarity also makes it an incredibly powerful solvent. You can dissolve a huge number of things in water. It is sometimes called the universal solvent. And again, this is essential for life. Pictured in the background here, far too small for you to read, is just a little bit of the metabolism happening inside our cells. Remember, I told you, you and I are mostly water. The solvent that exists within us is water, which means all of those molecules that make us tick, that do all the chemical reactions that drive life, are happening in water, which means all those different things can be dissolved in a single solvent in water. That's really a remarkable solvent. And once again, life would not exist were it not for this. And what makes it a great solvent, again, is its polarity. Now, there is a dark side to the fact that water is such a great solvent, and that is it's very easy to pollute, because almost anything that you put into the water, on purpose or not, is going to stay in the water because it's such a good solvent. This is why there's so many concerns with heavy metals like lead or arsenic being in water, because it just stays in the water indefinitely. Same goes with disinfectants will stay in the water, or microbes like COVID-19 microbe will stay in the water, or all the pharmaceuticals that you and I take, they end up in our wastewater and they just stay in there. So water's super easy to pollute. Now, that might be some bad news about water, but let me tell you, as we get near wrapping up here, some good news about water. One important thing to know about water is that you can't use it up. We talked about water supply and the huge strain on the water supply, but the fact is the amount of water on Earth is not changing. The water we have on Earth has always been here, always, and what I mean is for billions of years. And it may surprise you to learn actually that scientists are still debating exactly where the water on Earth came from originally. You'd think we would have that ironed out by now, but it's still the subject of scientific research. We know the general sources of water, but it's sort of the relative breakdown of which was larger and by how much is what people are still studying. One of the major sources of the water on Earth is from above. In the early days of Earth, the surface was too hot and there was no atmosphere, so there was no water on the surface. But as the Earth started to cool and it was being bombarded by objects from outer space, those objects brought water with them. And much of the water that we have on Earth came from this source. Another major source for water, rather than being from above, is from below. There was a lot of water locked up in minerals in the core of the Earth. And then over time, tectonic activity, spreads it around, volcanoes erupt, releasing lots of water vapor, ultimately forming part of our atmosphere and so on. And so a lot of the water came from below. How much came from where still is being researched. But the point is, it's been here a long time. It's not going anywhere. Now, since that water is so old, it actually tells you another important piece of good news about water. When you take a drink of water, every atom, all that hydrogen and oxygen and that H2O in that water has been in a lot of places in its long lifetime. At some point, that hydrogen and oxygen has been inside an oak tree sometime in the past. It's been blasted out by a volcano, and it's been urinated by a dinosaur, which it's a little silly to think about, but it's true. We're all drinking dinosaur pee when we drink water, which sounds gross, but it's an important piece of good news about water, which is that it doesn't matter how dirty you make water, it can always be cleaned. Mother Nature has been doing this through the water cycle for eons. It gets cleaned naturally, but that's kind of a very slow process to wait for Mother Nature to clean it up. And we're using water kind of faster than Mother Nature can do this, but we can clean it up. We have all kinds of technologies that allow us to clean water, and we are getting more and more efficient at doing that. And I don't have time to tell you about all kind of the cool state-of-the-art work that's going on in this space, but if you want to see some examples from the organization where I work, Argonne National Laboratory, you can go to www.anl.gov/water and see some highlights of some of the water research going on there. And that's just one institution. There are research organizations all over the world, including probably all of the institutions that you guys represent, doing fantastic research, coming up with ways to more efficiently or more effectively take dirty water and turn it into clean water to address this huge societal risk we have going forward. So I told you at the beginning that water is invisible. It's not just the water that we drink out of a glass or that we shower with or that's in the toilet when we flush it. Water's in everything that we interact with every day, our clothes, our electronics, even the electricity that's powering the lights and the computers and everything else. All of these things require water. There is nothing more important that we have on Earth. And if we really want to have a sustainable future for water, we're going to have to make it visible. We all have to start seeing water in all of these things. And I'll just end by showing you this book here. This is a book that, as far as I know, is the only book ever written by 3 Seths. So I wrote it with a friend and colleague of mine, Seth Snyder. And then since we already had 2 Seths, we went to Seth Siegel. You may remember his name from a little earlier in my talk. He's also an author, fantastic one. He wrote a New York Times best-selling book called Let There Be Water, which is about Israel and the fascinating story about what Israel's done with water and how innovative they've been. And he also wrote that more recent book called Troubled Water. But we got him to write the foreword to our book just to make sure we could have 3 Seths. And what this book does is it goes through, it's written for a general audience. You don't need any scientific background or anything to read it. And it covers water from kind of all aspects, kind of an introduction to the science of water and biology and chemistry and physics and geology and all of that, but also traces water's role through human civilization, like the story from Mesopotamia I told you earlier, but kind of tracing it all the way from the dawn of human civilization to today. Talks about water technology, water and culture, water pricing and policy. So sort of a holistic view, high level read on water if you're interested. So with that, I will wrap up and stop sharing my screen. And I'm happy to answer any questions y'all may have. Thanks for paying attention.
Yay, thank you.
Thank you.
Seth, as you were talking, we have ongoing list of questions that people have been populating. So we have a good set of questions for you. And for those who have not added to it, take a look at all the questions. Feel free to put a star if you also want that question to be asked or add an additional one. So the first question that we have for you, Seth, is